Yes. Hello. Thanks everyone for coming. And let me introduce our speaker. We're joined tonight by Chris Wüthrich. He's an associate professor of philosophy at the University of Geneva, and he specializes in philosophy of physics. His current research focuses on the philosophical foundations of quantum gravity. Together with Nick Haggett, he wrote a book, Out of Nowhere, The Emergence of Spacetime in Quantum Theories of Gravity, which will become available early next year. So thank you so much for coming. And so could you tell us a bit about your new book?
So thank you very much, and thank you for having me. I don't know how long you want me to speak, but I'll just start, and you interrupt me with maybe questions or special requests. So the book is about a particular insight that quantum theories of gravity seem to be suggesting. As different as they are, these are approaches in physics which try to bring together relativistic physics, space-time physics, classical gravitational theory on the one hand, with quantum physics, and try to formulate a quantum theory of gravitation, possibly of space-time. And so string theory, loop quantum gravity, causal set theory, there's a number of approaches in that domain which are very, very different from one another. But one thing that they all seem to suggest in different ways, but nevertheless, that's sort of shared by these approaches, is that the fundamental structures that they postulate to exist, their ontology, does not seem to be spatio-temporal. So classical relativistic space-time, as we know and love it from general relativity, does not seem to be part of it. In fact, the structures postulated are quite different from anything we know from relativistic physics. Now, space-time does have to re-emerge in the sense that we know that our experienced world is, to a very good approximation, manifestly spatial and temporal. And we know that the best theories that we have about the structure of space-time general relativity clearly is a space-time theory. So there must be a sense in which whatever the fundamental structures are like, there must be something emerging from these structures at the appropriate scales that looks very much like a space-time. So in the book, we say a bit about what space-time emergence in general is and why it's important to secure that. And we then start out by giving a general template for how to think about space-time emergence, for which we use the concept of space-time functionalism, which we define and characterize and discuss in chapter 2. And then with that tool in hand, we go to different approaches. In particular, we look at 3 main approaches to quantum gravity: causal set theory, loop quantum gravity, and string theory. And for each one of them, we show how space-time disappears in these approaches, and then how, or at least sketch, how it could be thought to re-emerge from these fundamental theories. Now, of course, these theories they're not complete theories. They're theories in the making. Physicists work on these approaches. They're active research programs. So we cannot pretend to have something like a final version of any of these theories. But nevertheless, they're sufficiently well characterized that we can at least start to outline how a story of space-time emergence would work for each of them. And so that's, in a nutshell, what the book is about.
Yeah, and I think on the physical side of things, one may heard this question, especially when one talks about string theory, one speaks of 10 or 11-dimensional strings, depending on which particular theory is being discussed. So one might have the impression that string theory preserves space-time, although it says that it's has more dimensions. So could you tell a bit about more about the strings of space-time, particularly in string theory?
Okay, Well, so string theory are the chapters for which my co-author Nick Huggett has been the first author, but I'm trying to nevertheless give you some of the reasons why you should think that the fundamental space-time structures are not really space-time as we think of them. And this has to do with something connected to T-duality. That's a strong reason to think that space-time is not fundamental. The reason is that T-duality is a duality, a relationship between two ways of characterizing the physics, which physicists take to be physically equivalent. So in other words, there are different ways of characterizing the same physics. And one way to do that is to have the physics that's apparently of large distances, and then think of the winding dimensions, these additional spatial dimensions in string theory, as very, very small. But it turns out that we can translate this entire physics into a dual picture in which the distances become very, very small. So the physics of the large distances can be translated equivalently to physics of very small distances. Now, there's a question in philosophy that other philosophers have debated how we should think of dualities. Is this a case of underdetermination? That is, do we have a situation in which we have two theories which are both empirically adequate, and they're in fact empirically equivalent with one another, and so therefore, as a realist, a scientific realist, cannot commit to one of these theories being real or true, or the way the world is. So is it just a case of underdetermination where we have more than one theory and we have no good way to decide between? Then of course you could say, like, well, we could of course have something more than just empirical reasons for preferring one of the two theories over the other. If they're empirically equivalent, there cannot be, by construction, empirical reasons to favor one over the other, but maybe there are theoretical reasons to one over the to prefer one or the other. Maybe because it's more intuitive or complies with some additional theoretical desiderata that we impose, and so on and so forth. A further way to deal with dualities is to say that no, but they're physically equivalent. So there's a sense in which they're really the same theory. It's just that on the surface, the way they're articulated, the way they're expressed, appears to be inequivalent. So what we need to find is a perhaps more fundamental, more conspicuous formulation of these theories in which we translate the physics. And then we can see that there's two ways in which now the two dual descriptions can emerge from something more fundamental. And then we should commit ourselves to the more fundamental thing. The approach that we take is more cautious than that approach. It's an approach where we think we should, as realists, be committed to those things, to those aspects, to those elements, or to those structures of the two dual descriptions which are present in both of them. So that seems to be capturing that thing which is somehow invariant. It's not an artifact of describing the physics like this or like that. It's something that they both share. So given that distance is not something that they both share, we shouldn't be realists about distance. We shouldn't think that physical distances are really there, fundamentally speaking. So it's considerations like that which lead us to argue that this 10 or 11 dimensional space-time is really a space-time. There should be scare quotes around it. It's not physical space-time directly as we know it from relativity theory or maybe from phenomenology. It's something else. It's something that's analogous or has certain similarities with relativistic spacetimes, but it's not physical spacetime. Therefore, we must understand from this how from this higher dimensional structure, then something like a four-dimensional spacetime can emerge. And of course, with it, the sort of notion or concept of distance that we are familiar with and that has been so successfully used, of course, in physics for a long time. So that's the sense in which this fundamental structure is not space-time, even though it sort of deceptively looks like space-time.
Yes, thank you. And you also said that your program is that of space and functionalism. So for those who may be not familiar, can you explain, well, the functionalism in general and how you're planning to do that with regards to space-time?
Okay, so I mean, functionalism is basically the idea that if something eats like a duck, if something swims like a duck, if something quacks like a duck, if something does all the things a duck does, all the sort of, performs all the functions, as it were, of being duck or acting duck-like, then we should say that is a duck. I mean, what else is a duck? A duck just is these sort of things. So space-time on this conception is just the functions it performs. The functions it performs in particular for us in general relativity. That's what space-time is. That means space-time does not exactly have to be everything it is in relativistic space-time, in general relativity. So it doesn't have to be continuous. It doesn't have to have the differentiable manifold that we know in GR. It doesn't have to have the specific properties it has in GR, but it has to perform the functions that relativistic spacetime does in physics in general, and of course in particular in the phenomenology, in the way that we relate these physical theories then to the world as we experience it, to measurement data, to observations, to results, and so on and so forth. So that is what spacetime is that which performs these certain functions. That gives us a list of functions. So that means it does need to give us some concept of spatial distance. That's the same as the concept of distance that we know in established physics, at least to a very good approximation that can only differ in imperceptible ways from the concept of classical continuous distance and sort of continuous geometry that we use, non-Euclidean geometry that we use to model that. And so that's the first step. You identify space-time by its functions like that. There may be, that's certain geometric functions, topological functions, things like that. And then in a second step, you go to the fundamental structures of quantum gravity, and you then show that these fundamental structures, whatever they are, whether they're like this 10 or 11 dimensional beast in string theory, or spin networks in loop quantum gravity, or causal sets, or whatever you have, these fundamental structures have the capacity to, at least under sufficiently beneficial, favorable circumstances, to play these roles. And therefore, we then say these structures may not be obviously intrinsically, fundamentally spatiotemporal, but they play at the levels at which they have to all these spatiotemporal roles, and that's everything we need, really.
Yeah, and so I think when Tim modeling discusses in philosophy of quantum mechanics wave function monism, so the view that everything which there is just a wave function which lives in a configuration space, he says that it's not enough to just point out that there are some formal features in your figure which behave like spacetime. So one particular example is that maybe if you consider a wave function in a 12-dimensional configuration space, you could say that it corresponds to 4 particles in Pg's spatial dimensions, but you could also say that this wave function actually corresponds to 6 particles in 2 dimensions, and so on. So could there still remain a threat that apart from our more or less familiar space-time, some other spacetimes which do not correspond to our phenomenological experience would also emerge in the theories of quantum gravity?
Yeah, so absolutely. So, I mean, it's important to keep in mind that what we're doing here is physics, or interpreting the physics, and it's not just mathematics. So we have to show how the fundamental structures, I mean, these are mathematical structures, that's at least, you use mathematics to describe them, how they can play these physical spatiotemporal roles, how they can be, as Tim Maudlin says, physically salient. And we show this, that in order to relate the fundamental structures of quantum gravity to something that resembles relativistic spacetimes, you need to put in place certain assumptions, certain bridge principles in some sense. And these new assumptions may be initially very controversial when you postulate them, but they're necessary for so that you can establish the connection. And we argue that it is exactly those bridge principles or bridge assumptions you need to establish that relation, which is endowing the fundamental quantum gravitational structures with physical salience. That is, it's showing that we're doing physics, that we're not just doing mathematics.
Yes, so and when you postulate these bridge principle, wouldn't it open like some sort of exponential gap if you can't derive the bridge principles from your fundamental physical figure, then so to say, where would they be coming from?
No, I mean, the idea is not that they somehow have to be derived from the fundamental theory itself. In a way, they have to be added to the fundamental theory. They're like interpretive principles in order which are necessary to make that relation, that connection. And a historical example that we use to illustrate what we have in mind is you may know 17th century physical debates between Descartes or Cartesians and Newton. So the Cartesians said, in order for there to be a physical explanation, in order for us to do physics, we have to explain everything in terms of mechanisms, some sort of mechanical pushing, shoving interaction between extended bodies. That's what physical bodies are. And all physics, any physical mechanism has to be explained like that. And then Newton comes along and postulates the law of universal gravitation. And he doesn't give us a mechanism, a mechanical somehow understanding of how the gravitational force is acting mechanically between the sun and earth, or between any two bodies. He just says, like, look, I cannot give you a hypothesis, as he calls it, about the mechanical underpinning or the causal goings on, physically speaking. I just give you a new theory, and it works. And initially, the Cartesians said, but that's just mathematics. What you're doing is mathematics. It's not physics. But the Newtonians were then able to show that no, there's very concrete, specific ways in which you can relate the mathematical apparatus of Newtonian physics, including the law of universal gravitation, to observations, to something manifestly physical. And you can do that in a way that's much more successful than any Cartesian attempt of delivering a physical theory. So this took some time, but physicists got convinced step by step that they had to not abandon Newtonian physics, but to abandon their previous conception of what it was to deliver a physical explanation, of a physical account of a physical phenomenon. And they had to widen their understanding of what physics is to include apparent actions at distance. And here too, we have to add principles which relate what initially looks just like mathematics to established physics and to ways in which we can manifestly call to the manifest physical world. And by doing that, we need some principles to get them. And it's by virtue, ultimately, of course, of their empirical success that these bridge principles will or will not be vindicated. And
Yeah, but
succeeds, then that's the program. The program's been completed.
yeah, but so then just clarify, these principles are just brute facts. They
Yes, they're in some sense brute facts. I mean, you don't postulate them out of nowhere, as it were. They're constrained quite a bit. So, for instance, in the case of loop quantum gravity, which is one of the three theories we look at in some detail, you have spin networks which look like abstract combinatorial discrete structures, sort of graph theoretical structures. That's a piece of mathematics. You use graph theory, use knot theory to understand these mathematical beasts. And then when you relate them to relativistic spacetimes, you must make certain interpretive decisions and assumptions to say that it's those sort of things which act like this and which are going to give rise to these sort of joint actions. And so you give then a geometrical interpretation of these structures. And that is something that you add to the spin networks. But you don't just sort of freely do that. You do that in a way that's precisely and quite in some detail required or forced upon you by trying to accomplish that match, because otherwise you're just not going to get the match. So this has to be finely tuned to get it exactly right. So it's not that these principles are arbitrary, but you're right. They're in some sense certainly added to the fundamental theory.
Okay, yeah, thank you. And I think I think this is an objection which was raised by Asfeld, but if you consider functionalism in the philosophy of mind, then you would functionalize mental states with reference to some old theoretical terms. So, for instance, one could say that pain is the state that tends to be caused by bodily injury to produce anxiety, and in the absence of any stronger conflicting desires to cause wincing or mourning. And in this case, both a functionalist and a dualist would be committed to some theoretical terms which are already familiar, such as bodily injury. But it seems like all of the terms we are familiar in our day-to-day lives are spatial temporal. So how could you functionalize space-time without reference to anything?
Mm-hmm. Well, yes. So the situation is not completely and fully analogous to the philosophy of mind, because in the philosophy of mind, perhaps you could say it's the physical theory, the neurological theory, which is going to be more firmly established and more sort of acceptable on physicalist terms. And we're using that as our starting point from which we are now going to explain mental states or mental entities in some functional way. And of course, in the case of spacetime, this is not how we proceed. We don't start out from the firm vantage ground or vantage point of a well-established sort of physicalist kosher quantum theory of gravity, from which we then recover the dubious and problematic sort of space-time features. It's rather that the space-time features are given and they're pretty firmly in place, and they play a well-established place in extremely well-confirmed physics. So that's not the dubious part. The dubious part in some senses, epistemically speaking, certainly the fundamental quantum gravitational structures that we're trying to get at. So as it were, epistemically speaking, the situation is not completely analogous. But in a sort of a theoretical or metaphysical way, perhaps it is more analogous. It is, if the fundamental theory is correct in describing the world at its most fundamental level, then we can explain how the world is as it appears to us. We can derive it because we can have a functional reduction of space-time to these more fundamental structures. And of course, epistemologically speaking, that means thereby these fundamental structures get confirmed. They're not confirmed in another way. So in a case of neurology, we have many other ways about, we cannot just theorize about the folk psychology and only use that to confirm neurology. We have all sorts of other means to confirm a theory of neuroscience. In quantum gravity, we cannot. We are firmly caught at the scales at which human beings are caught, which are the scales at which GR is a very good theory. So, epistemically, that's much more certain in any way than the foundation. So there are disanalogies, you're quite right. We're not claiming that the situation is fully analogous, but it's a tool. The functionalism is a tool that we borrow from philosophy of mind and adapt it to our purposes.
Yes, but so maybe just to clarify, I don't understand how would you do this philosophically, because in the philosophy of mind, we begin with some theoretical statement of X, and then we would replace the mental states with free variables, and then presumably show that some neurological states can play the same role, but in physics, as you said, space-time plays an important role with in our currently developed thesis, but it plays role. The role it plays connects to some other spatial temporal objects, and it seems like we don't have the spatial temporal objects either. So if you were to try do the same trick that Louis suggests for spacetime, it seems like you would just end up with a theoretical statement, which is a bunch of free variables, and it's not clear how you could proceed beyond that.
Mm-hmm. So, I mean, but what is space-time? The functionalist says, like, let's say what space-time is. Well, space-time is that thing which gives me, spatial distances, spatial betweenness, nearness, neighborhood relations, what have you, these sort of things, and similarly for temporal relations, and so on and so forth. And now and you're telling me, well, what is this fundamental structure? This is not space-time. This looks very, very different. But then I show you, but look, space from this fundamental structure, which is not spatial in any meaningful way, sense of the term, nevertheless, if sufficiently many fundamental degrees of freedom interact in the right way, then what we have is we can have a well-defined notions of space, of distance, of betweenness, of nearness, of something like a spatial topology in some sense, and so on and so forth, is coming out from the fundamental theory. So what else do I need to show you to convince you that this fundamental structure is what ultimately space-time is? If anything, you tell me, space-time does for us in the physics lab, or maybe in the theories of when we do calculations and make predictions of what we're going to observe in a physics lab. If we can do all of that using the fundamental theory, at least in principle, then the functionalist claims that's everything we need to show.
Yeah, so you would say that notions, so you would say that when you talk about space and functionals, you show how some notions such as distance can be derived from the known spatiotemporal structure, rather than how can behavior of some objects with regards to space-time be derived from the non-spatiotemporal physical figure.
Yeah, basically that's it. I mean, the way the story goes is a bit different for the different approaches to quantum gravity. So, you know, in causal set theory and loop quantum gravity and string theory, it's not exactly the same story. So we're not doing exactly the same analogous thing. But yes, basically that's what we do. We sketch how something like a spatial topology or spatial distances or spatial areas or volumes or sort of, you know, something like which starts to look like a geometry can emerge from a fundamental structure that is not geometrical and doesn't have a space-time topology. And you know, if you have all of these things, then presumably you have all the geometry you need. Now, about physical bodies, there's a question what exactly is going to happen to physical bodies. String theory is a theory with the big ambition of unifying all the fundamental interactions. So in principle, from string theory, we should get out a theory of quantum gravity, but also something like the standard model of particle physics, which is the foundation for, you know, for the constitution of bodies, and which gives us then an understanding of how, you know, the physical bodies that we have around us come to be. Now, in loop quantum gravity and in causal set theory, the ambition is much less than that. So there's no obvious way, at least, in which you also have something like the standard model coming out of that. So in order to understand bodies and the way quantum gravity relates to physical bodies, you would need to add the standard model or something like the standard model, and then show how maybe, you know, the fundamental particles in the standard model interact with quantum gravitational degrees of freedom. But this is not something that's been worked out in these research programs. I mean, there's some sort of, you know, initial ideas of maybe how that could be done, but not more than that.
Yeah, I see. And I think on maybe somewhat different now, when we're dealing with quantum gravity, both as physicists and as philosophers, how important would you say for us to know the correct interpretation of quantum mechanics?
So sorry, to understand what?
To have the correct interpretation of quantum mechanics.
Oh, right. Okay, good. Yeah, that's a very good question. It's not something that we really address in the book, but I agree that it might interact. I mean, different physicists have different views about that, as maybe you know. Most physicists working in quantum gravity think that the measurement problem and interpreting quantum physics is sort of orthogonal to the problem of quantum gravity. So in quantum gravity, we just are in the business of generalizing quantum physics to a way in which it can accommodate gravity. And then, you know, once we have that theory and we show that it's empirically adequate, we can debate about the interpretation. But some people like Penrose, for instance, think that we can really only make progress in quantum gravity if we have a correct understanding and interpretation of quantum physics already beforehand. And in particular, he thinks that it's going to be gravity, which is what induces collapses of the wave function. And therefore, there must be some sort of deep underlying connection between one particular way of understanding quantum physics in terms of collapses and the project of quantum gravity. So that's a huge question that we sort of sidestep in a way. But there's a sense in which, of course, it pervades all of the the work, the entire book. Because if you think about it, what we're trying to understand is how, from some fundamental quantum structures, so this is quantum physics throughout, we want to understand how something like classical relativistic spacetime emerges. So surely we must have an understanding, therefore, of the emergence of classicality, of a determinate geometry from something that's quantum, right? So I completely agree with that. It's something that's throughout the book, in a way, it's in the background, it's always present. And we just assume that there's a way to deal with that. But the reason why we do that is just because, honestly, we don't know whether we can, it's a very hard problem. We don't know what we could contribute to that problem.
Yeah, because philosophically speaking, it seems to me that for instance, you have Boltzmann mechanics, which states that in addition to wave function, we have also an unobservable configuration of particles, and these particles live in 2G-dimensional space. And so if their Boltzmanns are right, then it might seem that when we extrapolate Boltzmann mechanics to quantum gravity, somehow we would end up with some fundamentally real space-time, but it wouldn't be that surprising that we haven't seen anything like that in, say, string theory so far, because the quantum mechanics on which string theory bases that does not itself contain anything like space-time.
Mm-hmm. So yes, good. There are some people who have taken one research program in quantum gravity, such as loop quantum gravity, for instance, and have then tried to understand, these in either sort of an Everettian way, perhaps, or a Bohmian way, and a Bohmian. So what we have in loop quantum gravity is our spin networks, these discrete combinatorial structures that I've already mentioned as the fundamental quantum states. Now, the thing is, of course, this is just basically a highly dimensional Hilbert space in which these combinatorial structures form a basis. So generically speaking, a quantum state of the fundamental structure is going to be a superposition of different spin networks. So there will not be a determinate spin network structure that's there fundamentally speaking, but it's a superposition of these things. Now, Bohmians have said, well, a Bohmian approach might be to say that even though it may not be, it's sort of hidden from us, it's like an additional degree of freedom, there may be a fact of the matter which one of these different superposition terms is in fact realized in the world. So that, there's, on top of there being a quantum state, being a superposition of this and that spin network state, there's an additional fact that really, in fact, the situation right now is that it's this one rather than that one. Just like, Schrödinger's cat is a superposition of alive and dead, but really, fundamentally, it means that it's one of the two, because that's a direct consequence of the particular precise determinate positions that the fundamental particles have.
Yeah, and so in this case, even though we have something like Bowman's, it wouldn't help us with the emergence of spacetime.
Well, no, they might. I mean, they would. That might be. I don't see any problem with getting the emergence of spacetime from a Bohmian understanding of loop quantum gravity. But the ambition that we have in the book is a bit more general. We try to articulate precisely and in somewhat more detail than is commonly in the literature, the way in which you can understand the emergence of spacetime also from a sort of generic, from the formalism, from the generic theory, rather than from a particularly Bohmian understanding of it. And in a way, maybe this is a harder problem because you have to first say how it could be that there are, such superposition states for which you don't even have a connectivity fundamentally that's determinate, but something that has to then emerge as well, some sort of classicality that has to emerge that's not present at the fundamental level. And there's, I mean, we look at some of the attempts that have been made in this direction, some understanding of which is analogous to an understanding of coherent states in sort of standard quantum field theory, as a tool to understand the emergence of spacetime, and using the coherence and the sort of the usual tools, and trying to see how far we get with that. All of this we argue, or we suggest anyway, maybe it's a bit weaker than arguing, but we suggest are going to be indispensable tools in understanding the classicality of the emergence of spacetime. But none of this solves the measurement problem. There's going to be, in one way or another, there's going to be the measurement problem that still needs to be addressed.
Yes, and so maybe if we continue to look at how quantum gravity and the emergence of spacetime can be connected to some other problems. Do you think that the problem of time having thermodynamic direction and the entropy increasing with time, it has of course also been quite controversial in the philosophy of physics, which would you think that it would have, so to say, a new shape or some new tweaks to this question once we come to realize that spacetime is in fact emergent?
Okay, that's a very interesting question. It's another hard question, of course. Now, I think the answer to that question will depend on the particular research program in quantum gravity. This may take different, different realizations or different forms in the different research programs. I'm not aware of people talking about how that might work in the context of string theory, so I cannot really address that, to be honest. I know that Carlo Rovelli, who's one of the main architects of loop quantum gravity, has a story of how something like thermal time with a time direction emerges if you have a sufficiently large system with sufficiently many degrees of freedom. In causal set theory, there is a very explicit way of adding in by hand, in a primitive sort of brute way, a direction to time. Because the problem is, causal sets, which just are fundamentally speaking a discrete structure which is partially ordered by a relation of causal precedence, that's way too general, because it's, there's just way too many structures which satisfy this very weak constraint or this weak condition. such that we need to impose additional conditions. And people who have worked in causal set theory, I should say, have toyed with the idea of introducing what they call a classical sequential growth dynamics. So you add in dynamical principles of how, in some sense, a causal set can grow. So there's some sort of primitive notion of becoming, of coming into being, that is brutally, primitively, fundamentally time asymmetric, because the structure only grows towards the future, as it were. It only grows in one direction, but not in both. And of course, the idea is that given this fundamental asymmetry that you put in the theory, that asymmetry would then explain the arrow of time macroscopically as well.
Yes, some philosophers, particularly those who, like John Ehrman, are skeptical of solving the thermodynamic directionality of time by stating that the initial conditions are just such that the entropy happens to increase in the universe. Would they then have reasons to prefer something like causal set theory because it admits time irreversible laws perhaps more easily than the competing approaches?
So maybe, I mean, that may be true for causal set theory, yes. For the others, I'm not sure. Probably not. So I think, there's likely that the same debates are then going to be had that we're already familiar with from that literature you cite.
Yeah, thank you. And you've brought up a bit earlier before the idea of classical sequential growth in causal set theory, and in philosophy, the features according to which the passage of time is genuine, such as presentism, according to which only the present events are real, and growing block theory, according to which only the present and past events are real. These features face some very significant challenges from the relativistic theory, which doesn't have anything like absolute simultaneity, but would Francis prospects be improved in quantum theories of reality and particularly in causal set theory?
So causal set theorists themselves think that they found a way to show that fundamental becoming and the fundamental notion of something like a passage of time would be compatible with relativistic physics. The way they solve the normal incompatibility between absolute, the loss of absolute simultaneity with a notion of passage or absolute becoming or something like absolute present or something like that, is to say that no, we don't have a universal global sense of becoming or a global sense of the now as opposed to the past or the future or something like that. What we have is what Raphael Sorkin, one of the founding fathers of causal set theory, calls asynchronous becoming. So it's out of synchrony. We have a structure, a tree-like structure, which grows towards the future in all the branches, as it were. It adds more to the sum total of existence continually. That's a fundamental physical process of becoming, but it does so in a way that there's no absolute synchrony. So there's no facts of the matter if you have what corresponds to space-like related events, an order in which these two events have become. It's not the case that they are absolutely simultaneous or that this one has become first and then this one, or that one has become first and then this one. And so there's no facts about that. So it's just sort of local becoming at each tip of each branch. And there's no sense in which there's a global notion of time ordering between them. That's the way this is supposed to be resolved. Now, a number of philosophers, including me and Nick Huggett, have responded to this idea and have tried to sort of explored it a little bit and have seen that, to a first approximation anyway, all exactly the same sort of debates can be had as we can already have at the level of general relativity. So of course you can introduce a notion of local becoming or asynchronous becoming in general relativity already. If you do something like a light cone becoming or a world line becoming, so things become along a world line, or things become by a sort of an absolute ordering of light cones, which have this sort of hierarchical becoming of inclusion. That is, every light cone includes all its past light cones along any path that goes through the tip of that light cone. So we can do these sort of things and say and sort of relativize becoming in ways like that, where we basically make use only of the Lorentz invariant structure of a relativistic spacetime. So we don't rely on any notion of absolute simultaneity, of course. So if you like these sort of approaches, then yes, something similar can be had in causal set theory as well. But the way in which causal set theory goes beyond that is very, very limited. So the conclusion for most philosophers, including for me, is that the block view, the eternalist picture, is still the most convincing interpretation of what's going on. So yeah.
Yeah, so if one does try to go beyond the idea of this subjective becoming and tries to utilize something like classical sequential growth, what would you make of the strategy to say that the G is always a fact of the matter about which of the two spatially separated events comes first, but these facts are empirically inaccessible, that we just can't tell for sure which one has occurred and
Well, okay, but that now to me sounds exactly like somebody who says, well, there is absolute simultaneity in a relativistic space-time. It's just that it's not empirically accessible. So there's all the different inertial frames, which are empirically on a par, but metaphysically speaking, there's one particular frame or maybe one particular foliation which is nevertheless metaphysically privileged. Now, of course, you can do the same move in causal set theory as well. You could say there are such absolute facts about which of two space-like related events occurs first, but that's something that you add to the theory, because it's not in causal set theory, it's not in classical sequential growth. It's an addition, it's a metaphysical addition to the theory. And other than your metaphysical intuitions, I don't see a very good motivation to do that, because nothing in the physics motivates that. There's absolutely, any such addition has absolutely no empirical trace. You have to be very clear about that. So I think this move is very unattractive for the same reasons it's unattractive in relativity already. And it's not the move that Faye Dowker and Raphael Sorkin, the two main proponents of asynchronous becoming, they're making. They're saying like, no, we don't add any facts like that. There are no absolute facts about ordering space-like events, but it's enough for there to be a sense of becoming.
Yeah, so I agree that it obviously does add something to the theory, but it seems like another problem for the view, if you try to do so in special relativity and say that one of the frames does capture the absolute present, Balashev and Yassen in their very powerful critique point out that this knowledge and fissure faces a huge explanatory gap, according to which the space-time is fundamentally Galilean invariant. It has some absolute notion of simultaneity, but all the dynamical laws just conspire to be Lorentz invariant, and there is this explanatory gap here. And of course, if you prefer the views of Harvey Brown, that we say that the dynamical laws are that which explain why space-time is Minkowskian rather than Galilean or some other weird space-time, then what Emergence suggests is, of course, just an impossibility. But it seems like would the same explanatory gap problems also be present in causal set theory, or would Emergence at least get a reprieve on that one?
Yeah, so that's a good question. I've never actually thought about that specifically. I do think that the same gap would be present there, because I don't see what would really fill that gap.
Yeah, I see. I suppose it would need some or more accurate, more exact formulation to be able to discuss more casually. So yeah, I think one last question from me would be a bit personal, perhaps, but over all of this research that you've done, would you say that would you say that some of the features of quantum gravity you find the most plausible or just the most appealing in some intuitive sense?
Oof. That's a good question. There's a sense in which I think all of the research programs that we looked at anyway have very attractive and interesting features. Otherwise, we wouldn't have bothered to learn that much physics and spend so many years thinking about their interpretation and the philosophical implications. So there's a sense in which they all have very attractive, appealing, interesting ideas, and they try to articulate a theory of physics based on these attractive ideas. Having said that, they all, without exception, face very, very big problems. And the problems are technical, they're mathematical. So in all of these research programs, there's huge gaps in completing the theory that have not been fully articulated, because often these problems are technically extremely hard. But they also all face conceptual philosophical problems, because much of what we have taken for granted and what is so intuitive to us is up for grabs in any of these theories. So all of these theories pose very formidable challenges to our intuitions. And finally, all of these theories have problems with somehow establishing contact with phenomenology, with some way of empirical testing or confirmation or disconfirmation. So there's a sense in which all of these programs, research programs, are not complete successes, quite far from it. So I don't know whether I would want to commit to any of them. Sometimes on Mondays, I think like causal set theory, wow, that's really cool. I should work more on that. And then on Tuesday, I think, wow, loop quantum gravity is really the way to go. That's so attractive and promising and amazing, and so on and so forth. But as a philosopher, I also think it's important for me to stand back and not. I don't have a horse in that race. It's not for me to somehow advocate one research program over another. I think this is the job of physicists to do. I see myself much more as a more neutral commenter on commenting on and thinking about the different approaches, and not maintaining some form of neutrality, which sometimes, precisely because there are no empirical tests of any of these programs, is important, because all of the physicists involved in these research programs, of course, they have to convince their institutions, they have to convince funding bodies to give resources to their approach so they can continue to work on these research programs. And so they all have a big sort of rhetoric in favor of their approaches and against other approaches. And for me, it's important not to be taken too much by that rhetoric and maintain that neutral stance. So I'm sorry if this is a disappointing answer, but it's at least an honest answer.
And no, actually, that it's that this features are, of course, very tentative, and so we can't really tell which one is correct so far. And yeah, so thank you for this, and we will now have some time for Q&A. So if you have some questions, you can come up here. So maybe if you just to my right, and then you can come up here, ask your questions, maybe have some back and forth. And
Okay.
yeah.
I don't see the room. How many people are there?
So we have like 10 people.
Okay. Hi, everyone.
Hello. Hi.
Hi.
Sorry, I'm not a physicist, so I don't really understand a lot of stuff very well. You talked about these sort of like localities and this like idea of local becoming. Like, what is it that makes something a locality? Like it seems like a really weird thing in terms of like defining that, or you know, yeah. What exactly does that mean?
So the idea is you have a partially ordered discrete structure, like, growing from one element, and now you add a second element. You have a second element to its causal future, or you put it sort of sideways, as it were, in a space-like related way. And then you have two elements, right? And then you add another element. And the rule is you can only add another element either to the future of existing points or space-like related. You start a sort of a new branch from scratch. And then you have these branches which may be interacting, because one point that you add may be to the future of more than one point that you've added earlier. And so in a sense, you can add more points and connections to what exists already to the future everywhere. But it's always local in the sense that you only add what's to the causal future, or what's to, something to the causal future of an already existing part. And you can add here and you can add over there. And then there's additions here and there, and there's just no fact of the matter now whether this one has been added first and then the other one, or the other one first and then this one. So that's the sense in which it's local. It's growing in both places, but there's no sense in which there's a global time passing that tells us which one of them were first. Just like there's no absolute simultaneity in relativity. That's supposed to be capturing this idea. I don't know whether that makes sense, but
Yeah, sort of like in terms of like our phenomenology in our like normal life, like am I in the same locality as like am I like in a slightly different branch to my friend or something like that? Or I don't really know how you'd relate this to like
sure,
things
yes.
on relativistic scales.
Yes. So, I mean, you and your friend are probably going to be not too far away in terms of relativistic distance. So the light doesn't take much time to travel between you and your friend. So strictly speaking, the becoming is local to you and to your friend. But since you're so close, there's going to be so many causal connections between your world tube and your friend's world tube, that this is not going to be humanly perceptible, that this will look like a global ordering of time frame. But now when we have much bigger distances, when you compare not you and somebody else on Earth, but you and some sort of creature on Andromeda or somewhere else, many light years away, then there starts to be a big gap, because it takes light now years to travel from one place to the other and back. So now there's a much more tangible way in which the becoming is sort of confined to smaller regions. And there's now absolutely no fact of the matter about what happens first, us discussing this problem here on Earth, or something space-like separation on Andromeda or somewhere there. Now, yeah, at terrestrial human scales, in principle, the same is true, but because the distances are so small compared to that, it's completely not noticeable. So this is exactly the way it is already in general relativity, of course.
Great. Yeah, thank you. That makes a lot of sense.
You're welcome. Thank you.
Hello.
Hi.
Thank you for the talk. I am also not a physicist, so my line of question will also be more on the philosophical side. I was wondering whether one might worry that this talk of space-time emerging might be a bit puzzling, or that the disagreement between somebody who denies that space-time emerges and somebody that says that space-time emerges is a bit verbal rather than substantive. So, perhaps someone might say that my conception of space-time consists of sufficiently general structural properties, and whatever object that you propose to say, this object has so and so properties which are structurally analogous to what we commonsensically think of as space-time. And this person might say, in that case, we've just found a different version, if you will, of space-time at the bottom of reality, as opposed to no space-time and then getting space-time emergently. So do you think that question makes sense, or
Yes, no, that question absolutely makes sense. And it's a question we've asked ourselves often, whether the question of space-time emergence is really just verbal, because it seems like there's a sense in which you could say, like, look, what physicists working on quantum gravity are doing is not showing that space-time doesn't exist fundamentally, but what they show is that space-time has, fundamentally speaking, a different structure from what we thought so far. And if you're willing to stretch your understanding of space-time just far enough, then of course you will be able to accommodate any weird quantum gravitational structure under the umbrella of space-time. And then we just have a merely verbal dispute. That's not interesting in that sense. What we show, or try to show in the book anyway, is that in order to pursue that line of reasoning, you really have to relax your understanding of space-time to a degree to which it starts to just have almost no recognizable space-time structure anymore. And in that sense, at least, it's not just verbal. The fundamental structures, which of course, in some sense, contain the seeds of spatial temporality, I mean, that's the project of showing the emergence of space-time, are nevertheless so radically different from something like phenomenological space-time or Newtonian space-time or relativistic space-time that we think it's the right choice to not call these structures space-time. So there's some justice in that. But of course, if you just say like, no, 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 I think, this is still space-time, then okay, call it space-time.
So what one may think that, one marker of emergence as opposed to a kind of, revelation about the distinctive characteristics that we couldn't imagine before might be that, say we think B emerges from A, and one marker that says this is an emergent phenomenon is you could have, so there's some modal variance, right? So you could have A but not B, but you couldn't have B without A. So is there something analogous going on in relation to space-time? So is this whatever the more fundamental thing is in our quantum gravity theory? Would there be some situations in which it would not be appropriate to speak of space-time existing at all?
Yes, that's an excellent question. This is something that we briefly touch upon in the book, and I'm currently writing a paper with somebody else in Geneva to try to articulate this idea more fully. It's exactly the reason why we then end up with the claim that space-time is contingent, because on any such theory, it could have been the case that the fundamental degrees of freedom, whatever exactly they are, combine in a way such that space-time does not emerge.
Yeah.
Such that there's nothing that resembles a spatial distance at our scales, or such that some other features of space-time are not going to be arising from the fundamental structure. So that's exactly right. And that's because that is a possibility according to these physical theories. I think it makes sense to speak of the emergence of space-time.
And one last question. So I don't know if you have firm opinions about broader metaphysics of emergence. So, some people might think that emergent phenomena are in some sense not real, or they don't really exist. And other people might think that, actually there's a kind of robust reality to these emergent strata of reality. Do you think, well, A, do you have a view? And B, do you think these kind of physical investigations give us distinctive insight into answering those broader questions about emergence?
So yes, I have views about these things, but I'm not so sure whether or to what extent the studying the physics gives us new insights into this question in particular. I do think it would be so first of all, it's emergent in the sense in the philosophical literature sometimes called weak emergence as opposed to strong emergence. It's a form of emergence that's compatible with reduction. It's not something that somehow is in no way reducible to the fundamental structure. That's not what we mean. But we still think that it deserves to be called emergence because there's a sense in which the macroscopic structure is genuinely novel and independent from the fundamental one, even though it is ultimately reducible to the fundamental one. So that's the sense in which there is emergence. And I do think that it makes sense to call the emergent structure real, just as, to the same degree anyway, to the same extent to which it makes sense to call our world spatio-temporal, even though fundamentally it may be some weird, complicated quantum structure. But it may, just like, you and me are real, the desk at which I'm sitting is real, and so on and so forth. It makes, I think it's kind of silly to say these things are not real. Of course, there are philosophers who would deny that, sure. I would not. I like to be very pragmatic about my ontological commitments about these things. And in the same spirit, I say like, no, what's emerging is real. Space-time is real. It's just not fundamental. That's a different thing, real and fundamental.
Thank you.
You're very welcome.
Yeah, so if no one else has any questions, then yeah, I think that will be it. Thank you so much for agreeing to this interview.
Well, thank you very much for having me. It's too bad I can't be here in person with you.
Uh,
Maybe on some other occasions.
yeah, I don't think there's like a lot of cables here, so and yeah, we already had a bit trouble with them, but yeah, I hope at least you could hear the applause. And
Okay, yes, thank
yeah,
you very much. Thank you.
thank you. Goodbye.
Bye-bye. Bye.